Hello everyone, and welcome to this explainer brought to you by Forge College. I am absolutely thrilled to have you here today. So in our last lesson on modeling and normalizing costs, we figured out how to map EVM gas and Solana compute units onto a totally level playing field, which is great. But you know, theory really only gets us so far. Because this is all part of our cost model synthesis capstone project, which sits inside the broader gas-first compute units course. And ultimately, that's all part of our massive track from EVM to SVM, transitioning from Ethereum to Solana. So today, we are taking those theoretical cost models and dragging them kicking and screaming straight into the laboratory for our current lesson, identifying and testing optimization opportunities. This is literally where the rubber meets the road, so let's get our hands dirty.
So, here's the million-dollar question. How do we actually prove our cost models are right? We've got all these beautiful, pristine spreadsheets predicting exactly how much we're going to save if we optimize our smart contracts, but how do we transition from those theories to hard empirical data? And, more importantly, how do we do it without accidentally blowing up our entire code base? Well, that's exactly what we're going to solve today.
Here's our game plan. First, we'll dive into the optimization lab. Then, we'll talk about prioritizing your experiments, building the benchmark harness, crunching the numbers, managing trade-offs and rollbacks, and finally, wrapping up the capstone. Let's get right into it.
All right, part 1, the optimization lab.
I really want you to adopt the mindset of a Web3 mad scientist today, but, a highly responsible one. In our lab, every good scientist needs a control group. In our world, we call that a baseline run. Basically, a baseline run is a rock-solid, time-stamped, and checksums starting point. It's essentially a snapshot of how your existing code performs right now. Because without this baseline, you have absolutely zero idea if your fancy new optimization actually improved anything or if it secretly just made your compute costs 10 times worse.
Okay, moving on to part 2, prioritizing your experiments.
Look, we definitely want to avoid those chaotic YOLO mainnet deployments. To do that, we need a really systematic way to pick our safest targets. We do this using 3 prioritization axes. First up, high expected impact, meaning is this actually going to save us meaningful gas or compute units? Second, low implementation cost. Is this a 10-minute code tweak, or are we talking about a massive 3-week rewrite? And third, minimal change risk. What are the actual odds this breaks our core application logic? We want to prioritize experiments that hit the absolute sweet spot across all 3 of these.
So, what do those sweet spot candidates actually look like out in the wild? Well, on the EVM side, you're looking for high-impact, low-risk targets. Things like reducing really expensive storage writes or packing multiple variables into a single storage slot to save gas. Now, over on the Solana side, you might want to trim down massive account sizes or maybe remove redundant signature checks in frequently used code paths to slash that compute consumption. These are the actual hypotheses that we're going to test in the lab.
Next up, part 3, building the benchmark harness.
Think of this as our workbench. If we want to test across both Ethereum and Solana, we have to extract cost data without spending real money. On the EVM side, it's actually pretty straightforward. We use the ethers library to do a dry run of the code via estimate gas using JSON RPC, which gives us the gas cost without actually broadcasting anything. On the Solana side, it's slightly different. We use add Solana/web3.js to construct a dummy transaction, assign a fee payer, call simulate transaction, and then we basically just parse the execution logs to get the exact compute units consumed. So, different tools, but the exact same goal, getting accurate, simulated cost data.
Which brings us to part 4, crunching the numbers.
Okay, so we have our baseline and we have our harness. Now we actually enter the execution phase, and we use a super strict optimization testing loop for this. Step 1, capture your baseline using the existing harness. Step 2, branch your code and implement just one minimal change in that feature branch. Step 3, run the exact same harness against this new branch. And finally, Step 4, compare the normalized results. Listen, if you change more than one thing at a time, you completely break the scientific method, and your data is basically useless.
When we're comparing those results, what we're really hunting for is the cost delta. The cost delta is just the quantifiable difference in normalized resource consumption, so EVM gas versus Solana compute units, between your baseline run and your experimental branch. A negative delta means you saved resources, which is awesome. A positive delta means you somehow make it more expensive. Whoops.
Let's move to part 5, tradeoffs and rollbacks.
Optimization isn't just about raw speed, right? It's about rigorously checking your work. To actually pass this capstone milestone, you need verifiable artifacts.
First, you need at least 2 experiments executed on their own commit branches, documented in a changelog. You also need your measured cost deltas stored in raw CSV or JSON files so that literally anyone can reproduce your before and after numbers within the noise bounds. And critically, you need a decision log entry detailing your trade-offs. This proves a reviewer can successfully follow your rollback steps to restore the baseline if things go sideways.
Because here's the thing. We cannot just eyeball these numbers. Web3 networks, even local nodes, they all have slight variations. If you see a 1% improvement, is that a real optimization, or is it literally just background noise? That's exactly why we run basic statistics. We calculate the mean, median, and standard deviation across dozens of runs. Then we perform a two-sided t-test to get a p-value of less than 0.05. We document the confidence interval, and we flag any inconclusive experiments. We want absolute statistical confidence that our cost delta is real before we ever recommend it.
And speaking of confidence, here is your safety net. You should probably memorize this. Always include a functional regression check and a documented rollback test to restore baseline behavior. No optimization, no matter how many compute units it saves you, is worth breaking core functionality. Your automated tests absolutely must still pass perfectly on your experimental branch. And if they don't, you need a clear, documented path right back to the safety of the baseline.
Finally, Part 6. Wrapping up the capstone.
It is officially time to bring all of these verified artifacts together into the final flow. We started back in Phase 1, modeling and normalizing costs. Today, we absolutely conquered Phase 2, identifying and testing optimizations to get that hard data. Next up is Phase 3, capstone report synthesis. This is where you'll package all your CSV files, decision logs, and cost deltas into a highly professional presentation. You're basically building a bulletproof case for your architecture decisions.
Before we finish, I want to leave you with this golden rule of software engineering. Measurable optimization requires a focused change, controlled conditions, and a reproducible pipeline. If you can master this discipline, you aren't just writing smart contracts anymore. You are engineering highly performant, undeniably cost-effective Web3 protocols.
And with that, your optimization lab is officially open. Huge congratulations on bridging that gap between theory and empirical data. This explainer was brought to you by Forge College. Please make sure to visit forge.college to continue your Web3 engineering journey and dive into Phase 3 of this capstone. But before you close this out, I want you to really think about this. If you could only pick one single optimization to implement right now, which one would yield the highest reward for your actual users? Keep experimenting, have fun in the lab, and I will see you in the next explainer.